Welcome. This summer I worked with Emily Kang on a problem in Riemiannian geometry. There are three frameworks. One is a smooth Riemannian manifold, which is compact. The second framework is a polyhedral space. It's a piecewise smooth Riemannian manifold, like a polyhedron. And the third framework is a billiard framework, which is a smooth Riemannian manifold with boundary. So here we have examples of smooth Riemannian manifolds with boundary. The definitions are here, or the question. First of all, we have on each of these manifolds, we have an exponential map, which is defined, globally defined by Hopf-Renoff. And we can then look at the wavefront, which is the image of the circle of sphere of radius t under the exponential map. So at the beginning, this is a nice sphere, but it becomes, wrapped around the manifold and becomes more and more complicated. Now we say that the wavefront becomes dense if it eventually covers, more and more of the space. Technically, this means for if you take a point Q and a ball of radius r, then there exists a time after which the wave hits that ball. So it's kind of a mixing type of mixing property. We are not aware that this has ever been considered, this question, for which manifolds this holds. So there are three possibilities. Either we have this mixing property for all p, or then we have the mixing property just for some p, some points where the wave starts, or we have it that it never happens. It's never dense. And here is a list of examples. So this summer we proved that for the flat torus, proved it for 2 dimensions, but it's obvious it works for the proof works for any dimension d, that here it becomes dense. For a general Riemannian manifold, we have no idea. The conjecture is, of course, that it would always happen, except in a few cases, like Wiederkehr cases or cases with some symmetry. Then for the polyhedral part, we looked at the case of a cube, and this cube case can be, billiard case also can be reduced to the torus. You just, here a little bit more subtle, the covering here is a non-abelian covering, but here it's just a nice universal cover. And for the case of where it happens in some cases, if you take an ellipsoid, and you start at the point where the symmetry line goes through, then it will just, the wavefront will go on the other side and come back. So it will, at this point, it will not become dense. We are not aware that this is has been proven that it actually becomes dense when you start at another point. There is no doubt about this. Also, with polyhedra, you can construct you take strips of spheres and you glue them together, and you can get, also in higher dimensions, you can get examples where this mixing happens sometimes and sometimes not. And for the solid round ball, which is a case where when you start at the center, the billiard at the center, then what actually happens is the wavefronts will always become circles and not grow in length and will not become dense. This is a case which has been studied experimentally, Niels Berglund, and he also informed us about some paper like Vicente, who has in 2020, they actually computed the length of the wave depending on the asymptotic length of the wave, depending on how far you are on the center. So here's the formula arcsine of the radius. If the radius of the disk is 1, that's the formula, and then that's the times t. So it grows linearly, which is to be expected, but it's kind of interesting that you have this this explicit formula. Now, in the case of where it doesn't happen at all, this is related to a classical problem of witih manifolds. You want to have every wave comes back to itself, so that's witih coming back, and it's happening for the sphere and the projective spaces. In the case, in two-dimensional case, I know it has been proven that these are the only ones, but I'm not sure what is the status of this Blaschke conjecture in higher dimensions. So it's clear that this has to be a very exceptional case. Now, kind of interestingly, for polyhedra, I'm not aware of any. I have not seen anything, where it kind of would indicate that it. So even the most symmetric case, like the cube, we don't know. By the way, we also don't know here, for example, for the icosahedron. There's no doubt that it works. I think these cases can be done similarly by a cover. For the dodecahedron already, I'm not sure how that would go. So it's an interesting problem, and also here in the billiard case, even the most basic billiard, like the billiard in a disc, the circular billiard, there it in general seems to become dense, but we actually also have not proven that, and it's an open problem what happens when you are in the disc. It's obvious from this result that it should happen because the length of these waves become longer and longer. The length of the wavefront becomes longer and longer and longer, and it would be a miracle if at some point it would not go through some disk. Also here, there is probably a simple way to see that, but we don't know. That's what I wanted to present today.